Hello everyone. Welcome to our unit on work and energy. And this is the first segment of that unit, and we're going to be talking about what work is. So we're going to be thinking about what it means for a force to do work and to think about how we can calculate it. So the first thing to keep in mind is that a body experiences a change in energy when one or more forces do work on it. And it has to move in order for work to be done. We would also say that a force does positive work on a body when the force and the displacement are partially aligned, and will do the maximum positive work when a force and displacement are in exactly the same direction. So we'll get into the details of this a bit later on, but for the moment we can say roughly that work is equal to force times distance. And you can see that if a force causes no displacement, there's zero work, and also if there's zero force, there's no work. And forces can do negative work if they're pointed opposite the direction of the displacement. So here's our actual equation for work if we have a constant force. If the force is at least partially aligned with the displacement, positive work is done. And the amount of work done depends on the magnitude of the force, the distance, and the angle between them, technically the cosine of the angle. Okay, so W equals FR cosine theta. And we'll talk a little bit more about where this comes from coming up soon. Now it turns out that forces can do positive or negative work. When this load goes up, gravity is doing negative work and the crane is doing positive work, because if I draw going up as D1, you can see that F and D for the crane are aligned, so it's positive work, but mg and d are opposite for gravity, so that's negative work. Likewise, when it moves downwards, perhaps D2, the crane will do negative work and gravity does positive work. So work in the SI system is the joule, which is the Newton times the meter. It could also be feet times pounds in a British system. In CGS, the unit that you see pretty often is called the erg, and this is actually used a lot in astrophysics. Dynes and centimeters and ergs are all very common for astrophys. And at the atomic level, work can be measured by electron volts. And as we'll study in E&M, work is equal to charge times something called voltage. So that's where the electron volt comes from. So as an example, let's say we have a droplet of water that's mass 50 milligrams. And if you think about this, milli is 10 to the minus third, and grams is 10 to the minus third kilograms. So we really have 50 times 10 to the minus 6 kilograms. And so here we have this drop of water, okay? And it's falling at constant speed under the influence of gravity, so mg, and air resistance, which is like a drag force we talked about in the previous unit. So after the drop has fallen 1 kilometer, which will turn into meters, find the work done by gravity and also by air resistance. So the work done by gravity is going to be Fr cosine theta, where F is the force of gravity, mg, and cosine theta is the angle between the distance and the force, which in this case is going to be 0. So we're going to have mg distance cosine 0 degrees. So you plug in mass, 50 times 10 to the minus 6 kilograms. Gravity is 9.8 meters per second squared. D in this case is 1,000 meters. Whoops, 1,000 meters. And the cosine of 0 is 1. So you work all of this out and you get just about positive 0.05 joules. Okay? Now what about for the work done by air resistance? Well, that would be Fr cosine theta for air resistance, but what's the angle between air resistance and the distance? Well, it's 180 in this case. So that would be Fd times the distance times the cosine of 180 degrees. But the problem is that we don't know what Fd is. Well, we have a hint in the problem statement. It's falling at constant speed. So if v is constant, that tells us that A is 0, and from our last unit, we can say that the drag force must be equal to mg. So it's the same exact force, okay? It's the exact same calculation, 50 times 10 to the negative 6, 9.8, 1,000 meters, and now we have the cosine of 180, which is negative 1. So we're going to get about negative 0.05 joules. Now here's something that's very important to note for later. The net, or the total work on the raindrop, is the work from gravity plus the work from drag, which is 0. And the reason that the total work is 0 is because the speed is constant. And we'll talk about this a bit later. Okay, here's another example. We have a sled loaded up with bricks, and it's got a mass of 20 kilograms. It's pulled at constant speed by a rope inclined at 25 degrees above the horizontal, and it moves a distance of 100 meters, and we have a coefficient of kinetic friction of 0.4. So we want to find a few things: the tension in the rope, the work done by the rope on the sled, and the work done by friction on the sled. Okay, so we want to actually go back to last unit and draw a picture of this. And so we have gravity going downwards. We're going to have normal force going up. We'll have a tension like so at 25 degrees. And we're also going to have kinetic friction. Now, this is going to get a little complicated because the normal force is not going to be simply equal to mg because of an upwards component from the tension. So we could say that this is Ty and this is Tx. Okay? However, since it's moving at a constant speed, that helps us set things up, and we can say, first of all, that F net in both directions will be equal to 0. And again, this is happening because we have constant speed, so A is 0. So this means Tx minus force of friction is equal to 0, and Ty plus Fn minus mg equals 0. Okay? Now Tx, here's our angle, is going to be T cosine 25. Friction is going to be mu k times F normal. That'll be equal to 0. And Ty is going to be T sine 25. And plus the normal force minus mg equals 0. So the problem here is that we have a system of two unknowns, F normal and tension. Now this is kind of review of last chapter, so I'm not going to take a lot of time to solve this right now, but we're just going to note that the normal force could be written as mg minus T sine 25 degrees from this equation. And then we can plug that in here and eventually solve that for the tension, which is going to be 74.4 newtons. Okay, so the tension will be 74.4. And again, I'm not really taking a lot of time for this algebra right now, but this is how we would set it up. Okay, so what is the work done by the rope on the sled? Well, the work done by the rope is going to be equal to the force, which is tension, times distance, times the cosine of the angle. And we just found that tension is 74.4 newtons. R is going to be 100 meters. and we're going to have the cosine of 25 degrees. So that's going to give us about 6,700 joules, okay, the work from the rope. And here's a cool thing. The work done by friction is going to be equal to the force times the distance times the cosine of the angle between them. And, whoops, let's go back. The force of friction you can actually find from up here. The force of friction is equal to Tx. So you take T and you multiply that by the cosine of 25, and that's going to give you Tx, which is the same as Fk. R is going to be 100 meters. So if you look carefully, we have the same expression so far. The last thing that we need to do is put in the cosine of the angle, which is the cosine of 180 degrees, because friction is going one way, but the velocity is, or the displacement is forwards. So that turns into -1, and we get negative 6,700 joules. And just like before, the total work done when the speed is constant is 0. So that's a common thread that we've seen in these two examples. Okay, now one application of work is in a pulley system. And so what happens is that even though we're doing the same amount of work, we can decrease the force by increasing the distance. And in this case, what we've done is by holding this mass up with 2 ropes, we're actually doubling the distance, so we're going to have half the force. And one application of this is when you see mechanics trying to lift an engine out of a car. And you're going to see like a complex pulley system that's kind of going back and forth, and there's like 6 chains holding up this big engine. I don't know if that's a good drawing, probably not, but the idea is that if we can spread this force out over multiple chains or ropes, then even though we're doing the same amount of work, we're vastly decreasing the force. So for example, in this picture, if the mass was 50 kilograms, instead of needing 500 to lift it, because that's mg, we would just need 250 on each of those ropes. Okay, so next time we're going to talk about the more mathematical definition of work as a dot product.